Howdy. We're going to be taking a look at Chapter 5, problem number 19, which I believe is on page 131. And in this particular problem, we have a very interesting situation. We have a hockey puck of mass capital M. It is rotating on a string, radius r, that is passing through a small hole in the table. And that hole in the table is connected to mass little m. And the hockey puck is going in a circle here, like so. And the mass m is apparently keeping it in place. And so the question is, show that the speed of the puck must be root mg r over big M. We look at this and we don't really have any idea how to proceed. And so we revert to what we always do, and that is free body diagrams followed by Newton's laws. So we're going to take a look at the hockey puck and also at the little mass M right here. What's interesting about this problem is that it violates our intuitions. Intuitively, we figure that if the mass M is hanging right here, then it's going to drag the hockey puck down with it, and the whole thing will simply be pulled to the edge of the hole. But actually, because the hockey puck is in motion, that motion will be enough to keep the whole thing suspended. Let's see why that is. We're going to analyze this from the reference frame of the table. In other words, an inertial reference frame. So when we do, we see that there's exactly one force acting on the hockey puck, and that is the tension in the string. And there are two forces acting on the mass M, and one of them is the tension in the string. Notice, same string, same tension, and also the weight of the hockey puck, of the mass M pulling down. Okay, now that we have the forces, we're ready to do Newton's laws. Over for the big mass M, sum of forces is equal to mass times acceleration. It's going to be big M times acceleration. And the sum of forces comes straight off the free body diagram, which is T. The acceleration is found by observing the motion of the puck. It is moving in a circle with a constant speed. Therefore, its acceleration is v squared over r. And that's that. Now over here, for the little mass, the sum of forces on little mass m is going to be T minus mg. And that is equal to mass times acceleration. But this mass, if we observe its motion, is not moving at all. So the acceleration is 0. And therefore we get the tension is equal to mg. Well, here we have it. Tension is equal to one thing, tension is equal to another thing, so those two things must be equal. mv squared over r is equal to m times g. And all of this is just the analysis that we do from free body diagrams and Newton's laws without even trying to solve the problem yet. But now we look at the problem that we're trying to solve, and the problem that we're trying to solve is to find an expression for v. So we go to our equation and ask, what is v? Multiply both sides by r, divide both sides by big M, and take a square root. Now in algebra class, you would be required to take a plus or minus square root, and in physics also. But in this particular case, the velocity, the speed, v, must be a non-negative number. So we consider only the positive square root here. And we are done. Well, that was interesting, but it doesn't really satisfy our intuition. We still feel that the mass little m ought to be able to drag mass big M down with it. So I'd like to come back and reanalyze the hockey puck from an inertia, an accelerating reference frame, from its own reference frame. Imagine that we use the hockey puck itself as a reference frame. Now we recognize that as an accelerating reference frame because it is moving in a circle. The way we would do this in real life is we would put a little camera on the hockey puck, maybe a GoPro or something like that, and it would simply go around with the hockey puck. So we would, as it points towards the center of the circle, we would see the center of the circle always in front here. And if we analyze this from the accelerated reference frame, we now have to add in a fictitious force that is equal to, but opposite to, the mass times acceleration of the reference frame. Now, the reference frame is accelerating with a value of v squared over r in the direction here to the right. So we are going to have a fictitious force that points in the opposite direction. That was kind of poor. Let's do that again. There's our fictitious force. And now, when I do sum of forces on mass m, what I get is T minus mv squared over r. And that adds up to 0 because the hockey puck is not accelerating in its own reference frame. Now when we solve this equation, we get T is equal to mv squared over r, which mathematically is exactly the same equation that we got analyzing in the non-accelerated reference frame. So your analysis, no matter what reference frame you choose, will always yield the same equations. What's different is the physical understanding. In the accelerated reference frame, we can see that we have two forces, one of them tension and one of them the fictitious force, that cancel each other out. And that is why the mass of the, that is why the hockey puck does not get dragged down. It is experiencing a fictitious force pulling it outwards.